In the previous lesson, we defined the idea of an algebraic expression. In this section, we're going to look at one specific type of expression that we call a polynomial expression. An example of a polynomial expression is 3x squared plus 4xy. So what's important to note here is that what we have is a number times a variable plus a number times a variable and nothing else. There's no square roots, there's no trig terms. We're not dividing variables, there's nothing involved there. It's just number times a variable plus a number times a variable. Now, when working with polynomials, what we often like to do is factor them. So first, let's define a factor. When two expressions are multiplied to get a third expression, the two expressions are called factors. And so as a simple of this, let's take this expression here, 2x plus 1. Now, one thing we could do is distribute the 2 across to get 2x plus 2. And so now we've got a new algebraic expression that we multiplied the 2 and the x plus 1 to get. And so the 2 and the x plus 1 are factors. Now, factors can be numbers, like the number 2, but they can also be expressions, like x plus 1. Now let's take another example and look at factoring this. So what we want to do is look at each individual term and ask ourselves, what can we factor out? Well, there's a couple of things that jump out at me about this. First of all, I note that each term has a factor of 2. So I could factor 2 out to get 2 times 2x squared plus x. Okay. Well, now I note that what's inside the parentheses, each of those terms has a factor of x. So let's factor that out. And so we have a 2x plus 1 times 2x. And so there we have a fully factored equivalent expression to what we started with. Now, here's another example that you're familiar with from high school algebra. We've got a quadratic term, Q-U-A-D-R-A-T-I-C, a quadratic. Quadratic means that we've got an x squared term, an x term, and then a constant. And so we want to factor this. And the common technique for factoring it is to write parentheses like this, put an x in the first position, and then our second position we want to put numbers whose product is 2, but whose sum is a positive 3. Well, plus 1 and plus 2, that does the job. And so now to check that this really does work, meaning these are appropriate factors, what we can do is to FOIL things out. So we go first, outer, inner, last. And when we do that, we get x squared plus 2x plus x plus 2. And so then we combine like terms to get x squared plus 3x plus 2. And so this really is an appropriate factorization. It really does work. When we distribute, we get what we started with. Okay? And that's a technique that we can always use to check our work. Just distribute. If we get what we started with, then everything works out. Now, here's another quadratic expression, but this one is not quite so simple. This one does not have a 1 in front of the x squared. Here we have a 6. The technique that we just used in that previous example only works when that leading coefficient is 1. If the leading coefficient is not 1, here's a little trick that we can do. Let's write this as two sets of parentheses, but instead of putting a x, we're going to put a 6x. And then we're going to divide by 6. Okay. Now, in these blanks here, we're going to find two numbers whose product is 6 times 4, which is 24. So the product needs to be the leading coefficient times the constant, and then their sum has to be 11. The 11 is the coefficient of the x to the first power term. Okay? So I think two numbers whose product is 24 and sum is 11. Well, how about a 3 and an 8? Okay, that does the job. Now let's try to simplify this a little bit more. Notice that in this first term, or first expression, both of those terms have a factor of 2. So let's factor a 2 out. Both those terms have a factor of 3. So let's factor 3 out. So we get a 2x plus 1. Now in this second set of parentheses, both those terms have a factor of 2. And so we factor that out to get a 3x plus 4. Oops, we're going to run out of room there. Okay, divided by 6. Now we've got 3 times 2 in the numerator. Well, that's 6. So the 3 times 2 cancels off with the 6. And we get a 2x plus 1 times 3x plus 4. And so there's our fully factored equivalent mathematical or algebraic expression. Now we can check that this really works again by foiling that out, see if we really get what we started with. Here's another example of factoring a quadratic where the leading coefficient is not 1. And so we'll set it up the same way. We're going to put a 12x plus or minus something times a 12x plus or minus something. We're going to divide that by 12. Okay? And now we need to fill in these numbers with two numbers whose product is equal to 12 times a negative 6, which is a negative 72, and whose sum is equal to a negative 1. Well, let's try, how about a negative 9 and a positive 8? Right? Negative 9 times 8 is a negative 72. Their sum is a negative 1. And so that should work. Okay. Now let's see if we can factor anything out. Well, it looks like we could factor a 3 out of that first term. And so we're going to get a 4x minus 3. And then we could factor a 4 out of that second term to get a 3x plus 2 divided by 12. And then 3 times 4 is 12. That's going to cancel off with that 12 down there. And so we get a 4x minus 3 times a 3x plus 2. And there we go. There's our fully factored equivalent algebraic expression. Now here's an example where we can combine a couple of different ideas. So I look at this and I say, first of all, well, all these terms have a factor of 2y. So let's factor a 2y out. And so what's left? X squared plus 8x plus 15. Okay. Well, now I see what's inside the parentheses is just a nice quadratic expression with a leading coefficient of 1. So let's try to factor that some more. So x plus or minus something times x plus or minus something. So now I need two numbers whose product is 15 and whose sum is 8. So let's go a plus 3 and a plus 5. And there we go. Now it's fully factored. Nothing more to factor out. Now one last example is a very simple example, but one that comes up frequently. Here we've got y squared minus 16. It's a quadratic expression, but it doesn't have the y to the first power term. Well, this one is special because notice that I could write this as y squared minus 4 squared. And because of that, we call this a difference of squares. We are subtracting two squares. And so one way I could, so the way to factor this, a little trick here. Let's say we have something squared minus something else squared. We're going to take the first something minus the second something times the first something plus the second something. And so there it's fully factored. Again, we could verify this by foiling this out and see that we really get what we started with.